All right, hello everybody, welcome back to another video. In this video, we're going to be taking a look at cis-trans and easy isomers. So in the previous or last video, I covered structural isomers. So I've covered this, so I'm not going to be looking at this today. I'm going to be looking at cis and trans isomers over here. And these are a type of configurational isomers, which is a type of stereoisomers. So in this video, I'm going to be looking at this over here. But in a future video, I will take a look at optical isomers and I will take a look at conformational isomers as well. But these two are topics for other days. I'm just going to focus on this one for today. So let's just get started with some definitions. What is cis-trans isomerism? Cis-trans isomerism is basically when two compounds have the same structural formula, but the groups are arranged differently in space around a double bond or a ring. And another requirement or a requirement for cis-trans isomerism to exist is that the molecule which is exhibiting cis-trans isomerism or which wants to should have two different groups on both sides of the double bond. Now, this is, of course, this is not applicable to a ring. Rings have slightly different cis-trans isomer requirements, and it looks a bit different. They don't need a double bond necessarily, but in a alkene which have double bonds, this requirement stands. You need two different groups on both sides of the double bond. Now, I'm going to clarify a few things over here. Why do we need a double bond in the first place to exhibit cis-trans isomerism? And if you ask that would be a very good question. Why do you need a double bond? Why can't single bond compounds exhibit cis-trans isomerism? Well, let's take a look at it. I'm going to draw a comparison. So here we have a compound, okay? So this is dichloroethene, right? This is dichloroethene. And over here, I'm going to draw dichloroethane. Oh, sorry. Now, for this compound, for dichloroethane, if I do this, supposing I do this, these two compounds are the exact same thing. This is still dichloroethane, right? These two compounds are the exact same thing. And what I have done is basically I have this carbon over here, this carbon, what I've done is that I have rotated it, right? I've rotated it so that the chlorine, which was previously on top, this chlorine, it moved to the bottom because I rotated the carbon. And that rotation happened, right? I don't require anything extra to do that rotation. No energy is required to do that rotation because of this single bond. In a single bond, the rotation is freely movable, right? You can rotate the bond however you like. And just like that, in an alkane, or sorry, a halogenoalkane, which I have over here, dichloroethane, I could just rotate this carbon and chlorine. Now the spatial arrangement of chlorine is different to this molecule, and this molecule, they both have different spatial arrangements, but the compound is the exact same. There isn't any difference in that. However, for this compound, which is dichloroethene, if I do this, now these two compounds are not the same. These two compounds are definitely not the same. There is a difference in these compounds. As you can see, the exact same thing that I did over here in this swapping, the exact same thing I did over here, I have also done over here. I have just rotated this carbon so that this chlorine atom is now at the bottom. But this, however, is not freely rotatable. You can't simply rotate that carbon. And why is that? Why can't we do that? And some of you may have guessed why. The reason we can't do that is because of the existence of this pi bond. So remember, double bonds are made up of a sigma bond and a pi bond, right? Now, in single bonds, you only have a sigma bond, and sigma bonds are rotatable. You can freely rotate sigma bonds. However, pi bonds, right, the electrons in the pi bonds, if you've done your topic 4 studies well, you would know that in pi bonds, the electrons exist above and below the plane of the carbon atoms, right? You have electrons existing above and below. That's for pi bonds. Sigma bonds is concentrated between the nuclei of the carbon atoms, the electrons, but for pi bonds, which the pi bond is the second bond, the electrons form sort of a cloud above and below the plane of the carbon atoms. And this particular cloud, this electron above and below this cloud, it prevents the atom and prevents the carbons from rotating. It's kind of, you could think of it like a blocker or like a barricade. It prevents the carbons from rotating. They're rigid, they're stuck in their position. So if I actually want to rotate this carbon so that it forms this where the chlorine is at the bottom and the hydrogen is at the top, if I want to do that, I actually have to input some energy. I have to provide energy for this reaction to take place in order for me to break this bond so that I can rotate it. And then, of course, the bond reforms. So that is in the theoretical sense. That is why cis-trans isomerism is only possible in these compounds, in compounds with double bonds. You can't have cis-trans isomerism in single bonded compounds, because even if you rotate even if you change the spatial arrangement of the atoms, the compound remains the same. There is no difference, right? It's freely rotatable. These two over here, these two examples, they are the exact same compound. There is no difference between them. These two, however, are not the exact same compound. There are significant differences between them, and I just explained what they are. So now, what about the second requirement? I'm going to remove this. Hopefully you have understood why double bonds are needed for cis-trans isomerism to exist. Now, let's move on to the second requirement. The second requirement states that in order for a molecule to exhibit cis-trans isomerism, there must be two different groups on both sides of the double bond. And before I get to this, I want you to first understand what cis-trans isomerism is. So if I showed you these two compounds, this and this, how would you label them as cis or trans? The simple answer is, if the groups, in this case, the groups are chlorine, because hydrogens aren't really considered as the groups, if the groups are on the same side of the double bond. So now you see that chlorine on both carbon atoms is on the same side, right? This would be cis. And I like to think of it, if you want to remember this better, think of it as sister. Sisters, that means they're on the same side together. Okay, that's just how I remember it. This is not what it stands for, by the way. It's just my analogy to help me remember it. And then automatically the opposite would be trans, where they're not on the same side. They're on different sides spatially. They're arranged differently. This would be trans. So that is cis and trans. Very, very simple. So again, if I showed you a molecule like this, I'm going to give you 2 seconds to guess if this is a cis or trans molecule. And you may have guessed it. This is a trans molecule because the groups are on different sides, right? One is below and the other one is above. Now I'm going to give you another one. Any guesses as to if this is a cis or trans molecule? Well, you may have guessed it. This is a cis molecule because the groups are on the same side. Now, let's move on to why you need two different groups to exist on both sides of on both carbons in the molecule if you want cis-trans isomerism to exist. Imagine I had this molecule. Imagine. Now, I do have two different groups on one side. I have chlorine and hydrogen. But do I have two different groups on the other carbon? No, I don't. So how can cis-trans isomerism exist, right? Cis-trans isomerism is based on the fact that there are two different groups on either sides, and that these two different groups that are there are either on the same side or different sides. So in this case, in this carbon, if I rotate this carbon, it doesn't really make a difference, right? Either ways, hydrogen will be present on both sides. So cis-trans isomerism cannot exist. Hopefully you understand what I'm saying, right? It doesn't make a difference. So you need both sides of the molecule, both sides to have different groups. So both carbons should have different groups attached to them. You can't have same groups. If you have same groups attached to one carbon, cis-trans isomerism cannot exist. Now, that is all for cis-trans isomerism. Hopefully I've explained that well. It is a bit difficult, challenging to explain. I did find some difficulty in trying to think of how I can explain it to you. But if this video has confused you, I'm extremely sorry. Please reach out to me, message me, and I will go into more detail explaining it to you. If you need more help, I'm always there. Now let's move on to the next part, EZ isomers. And this is just a carry on from cis-trans, EZ isomers. Okay. I showed you in cis-trans isomerism where molecules look something like this, right? You can classify that as a cis or trans isomer, right? This would be a cis isomer because the groups on the same sides. But this also depends on the fact, cis, you can only name compounds as cis or trans if you also have groups on both sides which are the same, right? In this case, we have hydrogen. Hydrogen is the same on both sides, and that is what allows us to make the distinction between cis and trans. What if I didn't have hydrogen? What if on both sides of the molecule, I had completely different groups? What if I had something like this? What if I had this? Now, how would you do cis-trans isomerism? Is it possible? No, absolutely not, because on this, all of the groups are totally different, right? They're all different from one another. So how do you do cis-trans isomerism in this case? Well, you can't. That's why we use another type of naming system to define these type of compounds, and that is the EZ naming system. Now, E and Z are two different letters that we assign to compounds depending on how the atoms are arranged spatially or groups. Now, the first thing that you need to do if you want to name a compound as E or Z, you need to assign priority numbers. Now, what is a priority number? The priority number basically states that the compounds or atoms which are attached to the carbon atoms, you look at each carbon atom individually, okay, not together. So on this carbon atom, I have an OH. Well, this carbon is attached to an oxygen. And this, on the other side, the carbon is attached to a hydrogen. Now, which has a higher atomic number? Well, obviously, oxygen has a higher atomic number. And since oxygen has a higher atomic number, we assign it the priority. It is as, oops, what happened over here? it is assigned as priority number 1. And hydrogen is assigned as priority number 2 because it has a smaller atomic number than oxygen. Let's look on the other side. Which has a higher atomic number, chlorine or fluorine? Well, according to the periodic table, chlorine has a higher atomic number. That's why we assign it priority number 1 and fluorine priority number 2. Now, hopefully you've understood from this that priorities are given on the basis of atomic numbers. So higher the atomic number, higher the priority. The highest atomic number that is attached to carbon gets the higher priority. So if the priorities are on the same side, like you see, both the priorities, which is 1 and 1, is on the same side, then it is a Z isomer. And I like to think of it as for Z, so it sounds like Zame. Zame as in same. I know it's a bit lame, that rhymes as well, but this is just to help you guys remember it. And now remember, Z does not actually stand for same. It's a German word. I do not know what it is, but this is just a helpful way to remember it. Now, if the priority groups are on opposite sides, if you have something like this, now the priority groups are on the opposite sides, and then this is considered as an E isomer. Now, what if you have something like this? What if you have something like this? What if you have some compound like this? How do you assign easy isomers to this? All 4 groups are totally different. So how do you assign easy isomerism or the naming system to this? How is that done? So obviously for carbon number 1, this carbon over here, it's easy, right? This carbon is attached to an oxygen, and oxygen has a much higher atomic number than hydrogen. So it gets priority number 1, hydrogen get priority number 2. Typically, hydrogen is always going to get priority number 2 if that hasn't been made clear. Now, what about this carbon? This carbon is attached to carbon, and it is on the other side, it is also attached to another carbon. How do you make the change? How do you decide which gets E and Z? Well, if you can't, then you move on to the atom which is attached to the next of the current atom. So if I just take this, if I just isolate this and I take a look at this, so it looks something like this. This is attached, this carbon is attached to a CH3. Oops, sorry. And then this carbon is attached to another carbon, which then is attached to another carbon. Right? Oh, oops, sorry, my apologies. Actually, CH5. But you see, if you want to decide which gets the priority, you take a look at the atomic, you take a look at the next atom which is attached to the first atom. So this carbon is attached to this carbon, and this carbon, and then again the same carbon is attached to another carbon. Now I can't of course make a distinction about who should get the easy name, who should get the priority based on this, because both of them are carbons. So I move on to the next atom. So this carbon is attached to another carbon. And this carbon, well, it's attached to a hydrogen. So this molecule over here is going to get the priority because the carbon over here is attached to another carbon, whereas the carbon on this one is attached to a hydrogen. And this carbon over here has a higher atomic mass atomic number than the hydrogen over here. So it gets the priority. So you basically move down, you trace the molecule until you get a difference between the two groups. And that's why this gets the second priority. Hopefully that makes sense. And this would be labeled an E isomer because the priorities are on different sides. That is it for this video. Thank you so much for watching. I know it can be a bit confusing, but if you have any questions regarding this concept, please feel free to message me on my social media. I'll be more than happy to help you. Take care of yourselves and goodbye.